Okay, welcome back. This is the second half of lecture 21. So we left off with stereochemistry and cis-1,2-dimethylcyclohexane. We'll talk about the alternate isomer here, which is the trans diastereomer. So in this case, the two substituents are on the opposite sides of the ring. And so we refer to that as the trans diastereomer. And so the question is, again, is this molecule chiral or achiral? And like the last example we looked at, it has two stereocenters. And so we can determine their absolute configuration. So this is with respect to the bottom stereocenter, you've got 1, 2, 3. And so that is going to be, the H is coming out at me. So this is going to be the R configuration. And the top stereocenter, we have 1, 2, 3. And so that is also going in the R configuration, okay? And so there are two ways to approach this. Again, we can use the line wedge or we can go to the chair conformers. This one's going to be a little bit more complicated. First, we'll start with the line wedge. And so remember that the rigorous method for determining if a molecule has chirality or is chiral is to draw the mirror image and then ask the question, is it superimposable or not? Okay, and so that's what I've done here. And so these two molecules are in fact non-superimposable. They are enantiomers. If you take the image on the right and say flip it over to try and get the cyclohexane rings lined up, what you find is that the methyl groups don't line up. And so these are enantiomers. Okay, and I can also get at this through the chair conformations. And so if we want to draw a chair representation of this molecule, okay, I've got this chair conformer, and I'll label the carbons again, okay? And it's going to be the same process to try and figure out if this is if this is chiral or not. We'll draw a mirror plane, and we will reflect the molecule. Okay, and then we can try and see if we can overlay this chair conformer onto the original one. And you can work through it. I'd encourage you maybe to consider building models of each. You're not going to be able to superimpose these, okay? So they're non-superimposable mirror images. And remember, for the other example, we did a chair flip to get to show that it was the same molecule. Here, if I chair flip, what happens? What happens is that the methyl groups end up in equatorial positions, and hopefully you can see very quickly that that will not overlay with the original structure. Okay. And so again, you can get there through the chair representation. It's oftentimes much easier to do this through the line wedge. Okay. And so we can extend this to 1,3 dye substitution. And there are two possible diastereomers. So we can have the cis and then also the trans. Okay. And we won't spend a lot of time on the cis. It has a mirror plane. And so the molecule is meso. Of course, these are stereocenters. But the trans lacks that mirror plane. And if I draw the mirror image of the line wedge representation, I have that structure there, okay? And you can try and overlay these, but you will not be able to. They are non-superimposable mirror images. These are enantiomers. Okay. And so we can also approach this from the chair representation perspective. And so let me draw it over here. Okay. And so I've got a methyl group up and then a methyl group down. And let me label carbons so you can see. So this is A and this is B here, okay? I can draw a mirror image. Okay, and you can try and overlay that mirror image, but you will not be able to. So if you rotate the molecule on the right by 180 degrees and attempt to get that on top, you know, the methyl group that's in the equatorial position won't line up. And so this shows us, this confirms at least that these are in fact enantiomers. Okay. And so the last possibility is 1,4 dye substitution. So we can have, again, two stereoisomers here. The one where the methyl groups are on the same side of the ring, and then the one where the methyl groups are on opposite sides of the ring. Okay, and so this is the trans, the other one is the cis, all right? I'm going to redraw both of these in their chair conformations. So okay, so again, these molecules, we're not comparing these molecules, we're asking the question individually, are they chiral or not? Okay. And this is a favorite trick question. So these molecules are totally achiral. And unlike the other examples, they actually don't contain any stereocenters. So even though I've shown lines and wedges, that doesn't mean it's a stereocenter. You have to arrive at that determination separately. If you consider this top carbon up here circled in green and start to prioritize substituents, what you find is that this one and this one are the same. This carbon and this carbon are the same, and then they come back together, right? And so there are not 4 distinct substituents around that carbon. And so that is not a chiral center. It's the same thing at the other carbon. There are only 3 substituents there, three types of substituents. It is not a chiral center. And so the molecule itself is achiral. There's no need to think about enantiomers or to worry about enantiomers. Faster way to get to this that you might be able to see is just to look at this structure and say, okay, I've got a plane of symmetry cutting right between those carbon atoms. Of course, we draw the line and the wedge offset so we can see them, but if we were looking directly down on the molecule, they would be right on top of each other. The CH and the H would be bisecting that plane at each carbon. And so that molecule then, by that analysis, is achiral. You can also potentially see that in the chair representation. So we can identify a plane now, the same plane, just from a different perspective, where the CH3 and the H bonds lie, and then the cyclohexane extends up and below that plane in sort of, an equal sense on either side, okay? And so okay. And a similar analysis will get us to the same answer with the trans diastereomer. So again, I can cut this molecule right down the middle in the line wedge diagram, or if I prefer to do it with the actual chair representation, I can identify a plane in which the CH bonds and the bonds to the methyl groups lie, and then the ring is the same on either side of that plane. And so this is also achiral, does not contain stereocenters. Okay, and so again, there's more than one way to skin a cat. You can approach this. You can approach these issues of stereochemistry with the line wedge representations. You can approach them with the chair. Ideally, you can approach them with both. And for these cases here, we look for the sigma plane of symmetry. Another way to do it would be to just take the time to go to each center and try and determine the chirality, and hopefully you'd arrive at the conclusion that those are not actually asymmetric stereocenters, okay? So the same logic and analysis applies to other ring sizes. And so if we consider a 5-membered ring, So cis dimethyl cyclopentane. There's a sigma plane of symmetry cutting right down the middle of that molecule. And so it is achiral. If you look at the trans diastereomer, that molecule doesn't have a plane of symmetry. Hopefully you can see that. If I want to be rigorous and convince myself that it's chiral, I can redraw the mirror image. Okay, and hopefully you can see that you can't overlay those two structures no matter how hard you try. So these are enantiomers. Okay, the trans diastereomer is chiral, and that actually reminds me to make an important point is, what is the relationship between the cis and trans stereoisomers? Okay, so they are stereoisomers that are not mirror images of each other. They are diastereomers. So the relationship between these is that they are diastereomers. Okay, the cis is a diastereomer of either trans enantiomer. Okay. All right, so just want to say something about cyclopentane briefly. We're not going to spend too much time on it, but it's also relatively common. Okay, and like cyclohexane, it doesn't adopt a strictly planar geometry. And so cyclopentane adopts what we call an envelope geometry. So in this geometry, you have a plane defined by 4 carbon atoms. So if I just circle these, gosh darn it, all sorts of things going on today. And then well, there's 1 carbon that is out of plane. Okay. And the reason that the envelope is more stable than the fully planar orientation is twofold. So one is that it allows the bond angles to get closer to 109.5. The second is that it relieves CH eclipsing interactions. And so if you look at the CH bonds that are nearest to the out of plane carbon, they're staggered with respect to the bonds at that carbon. Okay, and so there's less torsional strain in the envelope conformer. All right, so in the last bit of the lecture, I'd like to talk about bicyclic systems. And again, these are very cool from a conformational standpoint. We first need to know how to talk about them. And so there are essentially 3 flavors of bicyclic systems: fused, bicyclic, and spiral. Okay. And so fused ring systems are ring systems that share adjacent bridgehead carbons or bridgehead atoms. So an example would be this ring system here. Okay. We call these carbons, oops, not what I wanted. We call the carbons that I've circled in green here bridgehead carbons or bridgehead atoms. And they're bridgehead because they bond to both rings. And because they are bonded to each other, they're adjacent. Okay, and so that's what we would refer to as a fused bicyclic system. The second type are just what we refer to as bicycles or bicyclic. And these are where the bridgehead carbons are not adjacent. And so an example of this would be this molecule here, or this molecule here. If you look at these systems, I've got two rings. One ring is here, and the other ring is here. Okay, in this case on the left, there's two 5-membered rings, and the one on the right, it's going to be two 6-membered rings. Okay, and the bridgehead atoms here and here and here and here are not directly bonded to each other. Okay, okay, and so that would be we refer to as a bicyclic system. The final flavor is what we call spiral, and these are where the two rings only share a single carbon or single atom. And so an example of this would be a situation where I had a 5-membered ring and then a 6-membered ring stuck together. There's one atom that they share in common. That's what we don't really call that a bridgehead. We call that the spiro atom or spirocyclic center. Okay. And so those are the three types of bicyclic systems. Okay. Within obviously there's an infinite number of possibilities of each. Within the fused subcategory, there's a very important one, which is known as Decalin. And a Decalin is fused 6-membered rings. So let me draw one without stereochemistry. Okay. So this is the backbone of a Decalin. Okay. What I haven't done is drawn in the stereochemistry at the bridgehead carbons. So this and this are the bridgehead carbons. And of course, they've each got 3 CC bonds, but they also have a hydrogen. And so I can put that hydrogen up or down. And if I put both hydrogens up, This is what's known as cis Decalin. Okay. And so this molecule is achiral. You can see that there's a mirror plane going right down the middle. Okay. We can draw cis Decalin through the chair conformers. It's going to look a little tricky because it's going to be two chair conformers fused together, but let's go for it. So oops. Okay, so that is an example. That's the chair representation. It's not my best work, but chair representation of cis Decalin. And the key point is that, you know, this may look chiral, but through chair flips, it's rendered achiral. Okay, and so even though you have this fusion, this molecule can still undergo a chair flip. And let me just make sure I don't mess this up because this is a little tricky. We're going to bring that one down. And so, right, so that's going to be axial. This is going to go here. Okay, you can draw a conformer like that. All right, and I want to point out the orientation of things. So let me clean this up a little bit. So here, this bond is axial. When I do the chair flip, it's equatorial with respect to the other ring. Likewise, this bond in the back here is equatorial in the initial conformer. But when I do the chair flip, it occupies an axial position. Okay, so you can build a model of these if you're unsure, and but essentially because you have the cis fusion, the second ring does not prohibit a chair flip. And if you draw an enantiomer for one of these isomers, what you'll see is that by doing that chair flip, you get to the same compound. And so the molecule is achiral. Again, this is an instance where it's much quicker to see it, I think, through the line wedge. The second one is the trans Decalin. And so let me draw that. So in this case, you've got one hydrogen up, one hydrogen down. Okay. You may be able to see from this structure that there is not a sigma plane of symmetry. I'll circle the bridgehead carbons again for you. There's not a plane of symmetry. And if I draw this in 3 dimensions, it looks something like this. Okay, and so that is trans Decalin. Okay, this molecule, okay, is conformationally locked. Okay, because of the nature of the fusion, you have 2 CC bonds in an equatorial orientation here. Okay, so these are this guy and this guy. And they're pointing on opposite sides of the ring of sort of the left-hand ring. So call this the A ring. Okay, so the way I've drawn it, they're di-equatorial. If you attempt to do a chair flip of the A ring, okay, don't let the Decalin structure confuse you. What happens when we do a chair flip? Everything that's axial goes equatorial. Everything that's equatorial goes axial. And so if I flip this, if I attempt to flip this, these green bonds have to go transdiaxial. And that is just not possible. Okay, and so the take-home message is that the transdecalins are locked in a single conformation. Okay, there's no chair flipping. So this is actually of great utility in terms of trying to understand and study cyclohexanes, because it does sort of freeze out the conformer and you don't have to worry about this conformational equilibrium. The trans isomer is also more stable than the cis isomer. And so if you just consider the A values in the cis isomer, I've always, no matter how I ring flip it, I've got one axial substituent in both chair conformers. And so that's going to be on the order of, let's call it a methyl group 1.8 kcals. In the in the trans diastereomer, both substituents are equatorial, and so you don't have that non-bonded interaction. Okay. All right, so that wraps up this lecture, and yeah, so this will be Friday's lecture. Tomorrow is a break day, and I will see you guys on Friday.